Hey everyone, welcome back to the channel. Today we are diving into one of my favorite software architecture topics, event-driven architecture, or simply EDA. It's one of those patterns that sounds a bit fancy at first, but once you get it, you start seeing it everywhere. In modern cloud applications, microservices, and even in the notifications you receive every day. What is event-driven architecture? At its core, event-driven architecture is all about reacting to events. An event is basically something that happened. For example, an order was placed, an event was completed, or a user logged in. Instead of having tightly coupled services that directly call each other, like a traditional layered or microservices architecture, EDA uses events as the main form of communication. Here is the magic. In EDA, each service acts independently. When something happens, that service simply publishes an event, kind of like shouting out, "Hey, order was placed." The service that emits the event doesn't know or even care who is listening, when they'll react, or how they'll process it. That's a big difference from traditional architectures, where one service directly calls another through APIs. EDA, on the other hand, is asynchronous and decoupled. Now, let's see how services communicate in EDA. You might be wondering, if there is no direct call between services, how do they communicate? This is where a message broker or queue comes in. Each service publishes event into a queue or topic, and other services that are interested in those events subscribe to them. They process the event whenever they are ready, completely independently. This makes the system highly scalable and fault tolerant, but it also introduces complexity. EDA isn't always the simplest architecture to implement, so before choosing it, it's important to understand its challenges. There are some key questions to ask before adopting EDA. To decide whether EDA is a good fit for your project, you should consider questions like, what's the difference between event and message? How can we avoid losing message? How many brokers or queue do we actually need? And how do we manage the status of our system when it's distributed across multiple services? Let's go through all of these step by step. Events vs messages. In EDA, the main concept is event itself. When an event occurs, we simply publish it and move on. The service doesn't wait for a response or care who handles it. It often calls fire and forget. In a message-driven system, however, it's different. You're sending a command or query to another service and expecting a response. That means it's more a request-response model. So event describe what happened and don't expect a reply. Message describe what to do and usually require one. In most EDA setups, we use publish subscribe or PubSub model, where one service publishes events and multiple services subscribe to them. In message-driven system, we often use point-to-point communication because we know exactly what service should handle the message. Now let's see how we can achieve avoiding message loss. Data loss is one of the biggest challenges in EDA. Imagine service A publishes an event to a queue, but right after that, the queue crashes and the data is lost. Or maybe service B reads the event but crashes before saving it into the database. The data is gone again. To handle these scenarios, we can use a pattern called event forwarding pattern. Here is how it helps. When service A sends an event, it first ensures the event is persisted in durable storage within the broker, not just held in memory. In service B, if service B reads the event and crashes, that's fine. The event is in the queue and can be reproduced later. To avoid multiple services reading the same event, we can associate a client ID with each message so the system knows who has processed it. However, this pattern has a trade-off. While it improves data integrity, it sacrifices some performance. Persisting data synchronously means slower throughput but higher reliability. So it all depends on your business priority. Do you value speed or safety more? Now the question is, how many brokers or queues do we need? You might wonder whether to have a single broker for all your services or separate ones per service or domain. In Building Revolutionary Architectures by Neil, Rebecca, and Patrick, the author introduced the concept of architectural quantum, an independently deployable component that includes everything it needs to function. If multiple services depends on a single broker, then your architectural quantum is effectively one, because if that broker goes down, all services go down with it. If each service has its own broker, then each can operate independently, meaning you have multiple architectural quanta. To find the right balance, you can apply the domain broker pattern. This means having one broker per domain. For example, if two services belong to the same business domain, can share a broker. This keeps domains independent but avoid unnecessary costs and complexity. Remember, more brokers mean better isolation and resilience, but also higher costs and maintenance overhead. The last thing to consider is managing a state in an event-driven system. State management is another tricky area. Imagine we have an order service that raises an event when a new order is placed. Other services like inventory or delivery react to that event and perform their part of the process. But what happens when someone asks, what is the status of my order? Since multiple services handle different parts of the process, the order's status is distributed. So how do we track it? There are two main approaches. One, push-based pattern. In this pattern, service updates a central status queue as it completes its work. The order service listens to this queue and updates its own database with the latest order status. The benefit is simplicity. You always have a single source of truth. As soon as one service completes its job, write its latest status into the status queue. So in our example, order service listen to this queue, update latest status in the database. However, the downside is that all services depend on that one queue, reducing your architectural independency. So your architectural quantum is 1. You might have already spent lots of effort and cost to increase your architectural quantum, but by using this approach, it will be bring back to 1. 2. Pull-based pattern. In this approach, you have a state service that listens to all relevant brokers and keeps track of status across the system. This service isn't part of the core workflow, so it doesn't affect other services if it goes down. It provides a centralized way to receive the latest status, but at the cost of maintaining another service. So because this service is at the center of your architecture and it just listens to the queue of other services, it will not bring down your architectural quantum, and we can get the latest status directly from this service, which is quite simple. Final thoughts: event-driven architecture offers amazing flexibility, scalability, and resilience. But it's not a silver bullet. It introduces complexity around data consistency, state management, and fault tolerance that must be carefully handled through patterns like event forwarding and domain brokers. If your system needs to react to changes in real time, scale efficiently, and handle asynchronous workflows gracefully, EDA is a powerful choice. Just remember, start simple, understand your domain boundaries, and grow your architecture as your system evolves.